Hi everyone, my name is Pablo Delgado and I am with the International Audio Laboratories in Erlangen, Germany. So together with Professor Jürgen Herre, we'll be presenting this work titled A Data-Driven Cognitive Salience Model for Objective Perceptual Audio Quality Assessment. And I hope you enjoy it.
Objective audio quality assessment systems had been used for more than 20 years for estimating speech and audio quality as an alternative to listening tests. They aim to predict perceived quality degradation of processed signals, for example by an audio compression algorithm, as it is reported in listening tests. So they can be employed in audio codec selection or real-time monitoring of quality, among other use cases. These systems basically allow us to save time and resources spent on conducting listening tests. The most successful objective quality assessment systems are based on perceptual models of human hearing, which are derived from psychoacoustic experiments. Here we can see a typical example of an objective quality measurement system, which will be the basis of our work. The system compares an unprocessed signal against a processed version of the same signal, the signal under test. The signals are converted into excitation patterns after a series of transformations. The excitation patterns are supposed to be closer representations of the audio signals within the auditory path. Here, phenomena like frequency selectivity of the cochlea and auditory masking are modeled. Afterwards, a series of distortion metrics are extracted. These distortion metrics serve as quality predictors for degradation in different perceptual dimensions, such as perceived band limitation, roughness, or noisiness. Some of the more advanced measurement systems can extract measures of cognitive effects as well. For example, predictors of increased masking thresholds due to processes happening beyond auditory periphery, such as informational masking. The focus of this work will be on what is known as the quality mapping stage in some quality measurement systems. The different quality predictors, the distortion metrics and cognitive effect metrics, are usually combined into an overall quality score to mimic the results of a possible listening test, evaluating overall quality over the same set of signals. So this metric to quality mapping stage is usually considered a basic model of auditory cognition, in which the importance of each degradation dimension in overall quality is expressed by the weights assigned to each of the distortion metrics in the mapping function. The way this mapping stage is implemented is usually with a multivariate statistical learning algorithm. These algorithms use listening test scores as ground truth to train the feature to quality mapping function. The used algorithms range from simple linear regression to more advanced learning algorithms such as artificial neural networks, support vector machines, and multivariate splines. So the learning algorithm uses subjective training data for two tasks. First, the learning algorithm needs to estimate a distortion feature to quality curves. The relationship between distortion metrics and quality is usually nonlinear due to peripheral hearing effects, such as disturbance detection and loudness compression. You can see from a typical plot of the distortion metric values against subjective quality scores that a nonlinear function fits the data with higher accuracy than a linear function. The second task of the learning model is to determine interaction between features. Interaction between perceived distortions are considered beyond peripheral effects and mostly cognitive. For example, the perceived severity due to spectral band limitation distortion in a signal may be eclipsed by more severe artifacts due to added noise, bursts, or modulation distortions. So these different distortion metrics do interact, and the learning model needs to find out the different degradation gradients at different points in the multidimensional feature space, so to speak. It is also known that reliable listening test data is expensive, and at most a couple hundred of data points are available at a certain time. These tasks may require models with a considerate number of parameters to fit, and overfitting may occur for the data sizes available. So based on the assumptions that we just presented, we propose an alternative mapping stage scheme. For our method, the mapping stage block of an objective quality measurement system based on the perceptual evaluation of audio quality, PEAK, a standard quality measurement method, will be replaced by a cognitive salience model. This model incorporates a perceptually motivated architecture that separates distortion to quality mapping from the interaction model. With these two aspects explicitly modeled, the mapping stage is expected to use the information from the training data in a more selective and efficient manner than general-purpose learning algorithms. So we firstly implement a separate distortion to quality mapping stage with basis functions describing degradation in different dimensions. Secondly, The interactions are modeled at a separate stage using the concept of auditory salience. Salience or saliency is described as the property of an auditory phenomenon that makes it stand out from other competing phenomena. As cognitive effects regulate distortion severity, they are also indirectly regulating salience when multiple distortion artifacts are causing quality degradation. For example, a cognitive effect may lessen the severity of a perceived artifact, and therefore this artifact will be less salient with respect to other competing distortions. The distortion to quality mapping is implemented through a set of independent basis functions linking one distortion's metric values in the feature domain to a scale in the quality domain. In this case, the functions were estimated by fitting the distortion metric values calculated over a set of signals with isolated audio coding artifacts at different degradation levels, for which listening test scores were available. The listening test method was based on the multiple stimuli with hidden reference and anchors, MASHRA, in which degraded signals are rated with respect to a reference, with scores ranging from 0 for the worst possible quality to 100 points for the best possible quality, usually meaning that the signal under test is indistinguishable from the reference. As band limitation was one of the isolated audio coding artifacts in the database, no band-limited anchors were used. And the fact that the signals contain only one type of degradation at different levels contributes to the independence of the estimated basis functions, as no interactions between artifacts influence their degradation scores. Finally, the individual basis functions were estimated using the multivariate adaptive regressive splines with a maximum number of 3 nodes per function that were allowed. The interaction part of the model assumes that cognitive effects regulate distortion salience. As such, the interaction part is implemented through a set of weights that depend on the outputs of the cognitive metrics. The cognitive metrics regulate the contribution of each distortion metric into the overall quality score at the model's output. Additionally, some cognitive effects may only start regulating distortion salience after its measured size crosses some detection threshold, and no longer influence salience as the measured effect size increases. This behavior is modeled through sigmoid functions, which parameters will be fit using data. The outputs of these sigmoid functions are termed here the detection probability weights. As not all cognitive effects will interact with all distortion metrics, the model parameter selection procedure only keeps meaningful interactions between cognitive effect measures and distortion metrics. The meaningful interactions will be based on the values of an interaction metric that considers all cognitive effect and distortion metric pairs, as measured on a listening test database. This database contains degraded signals with many competing audio coding artifacts stemming from real codecs. This same database will be used to fit sigmoid parameters so that they optimize the values of this interaction metric. The interaction metric is defined as the correlation coefficient between the values of the cognitive effect sizes, modified by their respective detection probability weights, and the values of a salience metric applied to each distortion measure. For a given cognitive effect and distortion metric combination, if the values of the cognitive effect strongly correlate to the salience measure values, it is assumed that this particular cognitive effect predicts the salience of the associated disturbance. Therefore, interactions with stronger correlations will be selected to take part in the model. So the salience metric is a function evaluated on the values of each distortion metric for the learning database at hand. It is defined as a correlation between a set of subjective scores and the distortion metric values. The metric only considers one signal at a time and all possible treatments within this database. So the stronger the correlation of a distortion metric to subjective scores is, the more salient the related artifact will be assumed to be. Two disjoint sets of subjective listening test data will be used. We use the first set of data, the calibration and optimization datasets, for selecting meaningful interactions between cognitive effects and distortion saliences, and for choosing the sigmoid parameters that optimize these interactions. This dataset contains 168 mean opinion scores. The second set is separated to validate the objective quality system on unseen data, to evaluate their performance in terms of prediction accuracy of the quality scores. This dataset contains 216 mean opinion scores. The used database corresponds to the Universal Speech and Audio Codec Validation Listening Tests,
It contains 24 different signals and 11 treatments of 3 different coding technologies at low and high bit rates. More than 25,000 individual scores have been condensed into mean opinion scores for this experiment. So here we can see an example of a cognitive effect interacting with the measured salience of a distortion metric, considering the subjective scores in the optimization database. The red line corresponding to the output of a cognitive effect metric, the probability of a signal being speech-like, can predict to some extent the salience of a linear distortion metric, plotted with the blue line across all signals in the database. The larger the effect size, the less salient is the distortion. It seems that for speech-like signals, linear distortion tends to be a less usable descriptor of quality degradation in this database. The orange line corresponds to a thresholded version of the red line when an optimal sigmoid transformation has been used to maximize the interaction between the cognitive effect size and the distortion salience. Here we can see the final selected interactions for the model. For the optimization database, meaningful interactions have been noted between linear distortions, noise, loudness, and missing components, and the probability of a signal being speech-like, for example. Also, we have found some interactions between 2 well-known cognitive effects that influence perceived distortion severity, such as perceptual streaming and informational masking, and the interaction with linear distortion metrics and noise to masking ratio metrics as well. Some interactions are negative, meaning that larger effect sizes will predict decreasing values of distortion salience. In the model selection, some interactions were included in pairs despite their weak individual interaction values. This is to contemplate a complementary behavior of some cognitive effects that have been reported in the literature. For example, informational masking has been known to counteract the effect of perceptual streaming, so the detection probability weight number 5 considers both effects at one time in a complementary manner. Here are the results for the final performance evaluation of some state-of-the-art objective measurement systems and some variations of our proposed system. We evaluated 2 variants of our system with the cognitive salience model, one without detection threshold modeling and one with optimized detection threshold models expressed by the sigmoid transformation. So the 2 proposed variants outperform an objective system that uses the same input cognitive effect and distortion metrics. This system, the DM plus CEM system, uses the same training and calibration data as the system using the cognitive salience model, but training an artificial neural network on the data. Note that there is at least a 6-point increase in correlation of the prediction scores against the actual subjective scores in the case of the optimized version. So to summarize the results of this work, we propose this cognitive salience model as a feature-to-quality mapping stage that explicitly models interactions of cognitive effects and distortion matrix saliences in quality perception. On a diverse set of unseen validation data, these 2 systems using the CSM outperformed a system with a general-purpose artificial neural network mapping stage with the same input features and training data. Also, these CSM systems also outperformed 2 state-of-the-art quality measurement systems that have been considered. Future work includes improving the model selection criteria, as some interactions were shown to be useful for the model despite a relatively weak interaction metric value. This is the case, for example, in the interactions that consider complementary cognitive effects such as perceptual streaming and informational masking. We, of course, need to validate the system on further unseen data with more diverse signal degradations. However, the preliminary results show that this may be a promising approach. Also, other beyond peripheral effects may be studied. For example, a metric that measures the release of auditory masking through frequency band co-modulation may be considered. Additional interactions of cognitive effects and distortion metrics for spatial audio are also worth looking into. So this concludes our presentation, and we sincerely thank you for your time. I'll be happy to answer questions and discuss the results in the poster session. Thank you.